Hello everyone. In last lecture, what we did, we completed the water prime numbers, 6k plus minus 1 representation of prime numbers, and uh, two, three methods we saw. One is primarity check in O of n after O of square root of n. So what we'll do today, we'll go with the sieve algorithm. Okay. So and sieve. Okay. So what it does, um, see if you have numbers like this. Okay, let's see, we have numbers till 25. We know 1 is not a prime number, okay? 2 is a prime number. Now what we'll do, we'll cancel out uh, all the numbers which can be divided by the 2. So like simply it's the table of 2, okay? 4, 6, 8, 10, 12. Like these numbers will get divided by 2, so we'll remove them, okay? 20, 22, 24. After that, now we have 3, okay? We'll cancel all those numbers which are divided by 3, okay? So 6 is already, we already roughed it, okay? So now we have 9, then we have 15, after that 21, that's it, okay? Now which number is not cancelled out? It's 5, okay? Now we have to delete all the numbers which can be divided by 5, okay? 10 is already divided, sorry, 10 is already cancelled out here, so only 25 is remain to delete, okay? Now we deleted the 25. Now we have 7, okay? Nobody is in the table of 7, and here's 14 already deleted out by 2. After that 11, we can see 22 is also already deleted. 13, here 26, we have numbers till 25. 17, 19, 23. Okay, so now you can see the numbers which are remain. Okay, those are the prime numbers. Okay, so this is Sieve algorithm. What it does, if number is not deleted, okay, what we do, delete its all multiples. Only two steps we follow here, okay? We go in a linear fashion. First, we took 2. We deleted all the multiples of 2. After that, after deleting all those factors, no, not factors, multiples, okay? After that, what we found, 3 is present, okay? It's not deleted. So what we did, we deleted all the multiples of 3, okay? 6, then 9, uh, of course 12 was already deleted, then 15, after that 21, okay? After that what we found, 5 is not deleted, and this way we did similar to all. Okay, and whichever are not deleted are finally the prime numbers. Okay, these are the prime numbers. Now how we will code it? Okay, let's move to that part. Okay, see, now what we are doing, uh, we are doing it in a range. Okay, let's take some range. Okay, we have like, and like we have, okay, till 100. So what we'll do now, here, see, here we are saving this thing in somewhere. Okay, we actually need somewhere a number 1 2 3 till that n number. Okay, on one place what we'll do, we'll say something 1 or 0, here 1 or 0, 1 or 0. What it represents, it depends on us. Okay, we can say 1 means it's a prime number and 0 means it's not. Okay, it depends on us. We can keep 0 as a prime also and 1 as a it's not prime also. Okay, so what we'll do now, we need a vector. Okay, we have vector of size. Okay, first vector of int, let's say sieve of size n. Okay, what we'll do, mark 1 as, okay, we'll assign 1 to each number. Okay, we'll consider that all numbers are prime. Now in the base, basically what we know as a base case, that 0 and 1, they are not prime numbers, we'll assign them 0. Okay, now we'll look from I equal to 2, I is less than n, I plus plus. Okay, now see, here what we did, if we found like, if we got a number which is not deleted. Okay, after that what we did, all its multiples deleted, we deleted its all multiples. So here in this vector, how can we know that the number is not deleted? Okay, if sieve of I equal to 1, what does it means? Not deleted yet, so it's a prime number. Okay, it's prime number. So after that what we'll do, delete delete its all multiples. Okay, so if sieve of I equal to 1, now what we'll do, for int j equal to 2 into I. Okay, like what will be the next first multiple? It will be of course 2 into I. Okay, j is less than n, and we'll jump with the gap of I. Okay, like 2, after 2 plus 2 4, 4 plus 2 6. Okay, and what we'll do, we'll assign that cy equal to 0. Like, we considering that we deleted it. 0, what does 0 means? 0 means deleted, which represents it's not a prime. Okay, so now what we'll do, now we have to see does we got the right answer. Okay, we'll go from 0 to n. If the value is 1, we'll print it out. Okay, if sieve of I is 1, it means that I is prime. Okay, so we have to print I. Let's see. Okay. Oh, Sieve of j equal to 0. See, we have all prime numbers from 1 to 100. 2, 3, 5, 7, 11, 13, 17, 19 till 97. Okay. So this is Sieve algorithm. And what it does, it takes time complexity of what we are iterating here for n, and inside what are we doing? For every n, we are going for like how many multiples of that numbers are in that range. Okay, like for 2 it will be n by 2, for 3 it will be n by 3, for 4 it will be n by 4. So basically, the time complexity goes like n log n, okay, in this case, and we can optimize it, okay. So let's move here, okay. Like last time, what happened? Uh, when we reach till like okay, from 11, what we saw, the factor of 11 22 was already deleted, okay, and whatever other factors, other multiples were above that 25 range, okay. Same for 13, for 17, for 19, for 23, okay. Those numbers, like in that range, okay, for the range of 25, there were no numbers which can be deleted by these numbers 13, 17, 19. Like 13 into 2, what it is, it's 26, okay. So 26 was after the range whatever we wanted, okay. So basically, if we can see that like uh, we have to just go till square root of n, okay. We have to go just till square root of n. This will be the case. Like see, 25. What is square root of 25? 5. Okay. So take any number which is prime after 5. Okay. And we'll see that does any multiple of that number exist which is not deleted. Like take 7. Okay. Here take 7. What is the next multiple of 7? 14. But it was already deleted by that number 2. Okay. 21. 21 was already deleted by the number 3. Okay. Now take what? 11. 11's next is 22. Okay. 22 was already deleted by 2. So uh, we have to just go till square root of n. Okay. And another thing was like see. Hmm, which number should I take in this case? Huh. Okay. Take this 5. Okay. Take this 5. Uh, the first number we deleted from the 5, okay, was actually 25. As you can see, it was 25. Go to the 4, sorry, 2. The first number which was deleted by 2 was 4. Okay. Go to the 3. The first number which was deleted by 3 was the 9. Because see, 2 deleted that number, 4 and 6 and then 8. Okay. So 6 was already deleted by 2. Okay, 2 already deleted that number 6. So 3 directly deleted the number 9. Okay, 5. Okay, for 5, 10 was already deleted by the 2. 15 was already deleted by the 3. 20 was already deleted by the 2. So what was there? Only 25. Okay. So from this, what we can see, also we don't need to start from 2i. Okay, like we started j loop from 2i. Instead of that, what we can do, we directly start from I into I. We can directly start from the square of the number. So we'll cross check. We'll cross check that is it working. Okay, so I into I will be less than equal to n. Okay, this case. Okay, I into I is less than equal to n, which is same as I is less than equal to square root of n. Okay, these both are same. Instead of square rooting n, what we are doing, we are multiplying, we are squaring that I and then checking is it less than or equal to n. And what? Okay, here we'll start from the square. Now we'll check. Does the answer will get right or wrong with this change? Okay, you can see nothing changed. But what changed here? The change was the time complexity. What happened here? Instead of going till all over n, we just went till square root of n, and here instead of starting from 2 into I, we started from the square. So actually, the time complexity will be here is n of log n. Okay, you can read the block from CP algorithms where they I think they proved this thing that how it's n log of log n. If it's there, I will provide the link of that blog. And yes, this is it. This is the code for C. This is the not most optimized. I think there are more advanced C optimizations, but this is normally works for around 1000, even 1700, 800 problems. Okay, 1700, 800 rated problems. Okay, what we'll do, we'll solve a problem. Okay, which is related to C, and it's very famous problem. It's on code forces and it is T prime C. The question says we know that prime numbers are positive integers that have exactly two distinct positive divisors. Okay. Similarly, we'll call a positive integer t prime. Okay, t prime. If t has exactly three distinct positive divisors. Okay. You are given an array of n positive integers. For each of them, determine whether it is t prime or not. Okay. So what we have number till 10 raised to 12. Okay, a number will be till 10 raised to 12, and what we have to do, we have to just tell that it's a t prime or not. And what is the property of t prime number? If it has exactly three distinct positive divisors. So let's try to solve it. Okay, so see what it says. The number n, it has three divisors. Okay, three divisors. It has three divisors. So what we know about prime numbers? Okay, a prime number has only two divisors. Okay, 1 and n. Okay, now let's consider we have this number. Okay, let's say n dash. Okay, so we have three divisors of this number. Okay, so divisors will be 1 and dash and some x. Okay, some x. But what we know that the thing we know is x is not equal to n dash, because okay, it's the wrong sign. Okay, what we know, x is not equal to n dash. If x was equal to n dash, then it's the prime number. The divisors will be 1 and x if x is equal to n, huh? And if it has two divisor, what it is, it's a prime number. Okay, so we know that we have only three divisors, 1, x and n dash. Okay, n dash is that number, okay, which is t prime. Of course, 1 will be divisor there, okay, and some x, okay. So if x is not equal to n dash, okay, but x is the divisor, so what will the possible n dash number can be? Okay, so see, we have 1, we have x, okay, and we already know that. Okay, take a number, like take 20. What's the prime factorization of 20? 2 into 2 into 5. So whatever divisors of 20 are can be created from this set. Okay, take anything, 2, 5, 2 into 2, 4, 2 into 10, sorry, 2 into 5, 10. Okay, then 5 into 2 into 2, 20, 20 itself. Okay, so we can create a divisor from its prime factorization. Okay, if we have prime factorization, we can create its divisors. Okay, so see, consider like that. If we have 2, okay, so what will be the next number 2 can create only by itself? 4. Next will be the 8. Next will be the 16. Okay, here what's the prime factorization? 2. Here 2 2 times. Here 2 3 times. Okay, here 2 4 times. Take another number like 3. What will be the next number 3 can create? Okay, by itself. It will be the 9. 3 into 3. So what we know that x is, okay, only another divisor to the n dash except n dash and 1 in itself. So what we can say here by the basic mathematics concepts of number theory, that we can create n dash only by x. Okay, so what's the minimum, like what will the first number which x can create? It will be the, of course, x square. Okay, after that it can create x cube, then x raised to 4. Okay, so if it says it has only three divisors, then what are they? 1, x, and it's x square. See, this is the these are the divisors of n dash. Okay, n dash itself equal to x square. X is its alone divisor, which is not equal to 1 or the number itself, and what remains? 1. 1 is that third divisor. Now what we got here? See, what we have now? We have 1, x and x square. Okay, these are the only three divisors. Now from this, what we can say, mm, x belongs to the prime number set. Okay, if we have set of prime numbers, x will be belong to the prime numbers. See why? Okay, consider any number, 1, 4, and what is 4 square? 16. So 16 doesn't have just 4 and 1 as its divisor. Okay, we have 2, 8. Okay, these are also divisors of 16. Okay, but let's take a case of any prime number, 1, 3, and what will 3 square? 9. 9 only have 3 and 1 as the divisors. cause 3 into 3 is 9. Okay, but here 4 was already 2 by 2. Okay, so the prime factors of that 4 will also be the divisors of the square of that number. Okay, if we have some number n, and n can be represented as x raised to y and z raised to a. Okay, and we have another number n square. So a number x, x raised to 2, x raised to till y, any combination from this. Okay, like we can say x into z, x raised to 2, z raised to a. Okay, all this combination, whatever we can create, will also be the divisor of this n square. So here this condition can be only satisfied the such numbers. Okay, we now we are talking about x square. Okay, x square is a number which is square of a prime number. Okay, and in question, what the range of number is from 1 to. Okay, now here we say, let's say n. Okay, a number n, 10 raised to 12. Okay, so if you have basic knowledge of about time complexity, so if we have constants till 10 raised to 12, we can't do O of n. Okay, we can't travel on 10 raised to 12 number from 1 to 10 raised to 12 and do something. Okay, it will give us TLE, time limit exceeded. Okay, so another option is O of square root of n, which is possible because what's the square root of 10 raised to 12? It is 10 raised to 6, and we can do 10 raised to 6. We can also do O of, okay, square root of n and multiplying it with log n. Okay, this is also possible because it will be approximately 10 raised to 8, and it will also pass. Okay, it will not give TLE. Okay, another is directly doing in log n. Okay, even O of 1. Okay, but we really don't know. Is it there any algorithm to solve this problem with this time complexity? Okay, we can try this. Okay, okay, see. Now what we know, if I have x as a prime number, okay, so x square will be the t prime. We know this thing. Okay, now if I have given number n, okay, and n is a perfect square. Okay, perfect square, like after we square rooting n, there are no decimal points, like take 3. Okay, 3, what will be the under root of 3? It's something like 7.23. Okay, 1.723. 2 for 2 root 2 is like 1.414. Okay, so these aren't perfect squares. Okay, because after square rooting, what we get a number with decimals. Okay, decimal point, like basically we get a float number, float value. Okay, take 4, what is root 4? It's 2. It's perfect square. Okay, so what we'll do, we have given n number and we have to check is it t prime or not. So we have to check, is it perfect square. If it's a perfect square, okay, yes, okay. If we get no, it means no. This number is not t prime. Okay. If yes, then what we'll do? We'll take under root of n. Okay. under root of n, and we'll check if c of under root n equal to 1, then we'll print yes, else we'll print no. Okay, this is simple thing, because if x square is a t prime, x is a prime number, and if we'll check for the x is prime or not, we can say that x square is t prime or not. Okay, so we have to check just for the root of that number, is it prime or not, and the time complexity will be around 10 raised to 6. We'll apply 10 raised to 6 um, c for 10 raised to 6, so it will be the n log of log n. Okay, here n is 10 raised to 6. Okay, not 10 raised to 12. Here for this time complexity it's 10 raised to 6. Okay, now what we have? We have a whole vector of size 1 to 10 raised to 6. Okay, where that index tells us that the number is prime or not. Okay, with that data, what we'll do, for every n, we first take its square root and check its value here. Okay, and we'll print out. So the overall time complexity for check doing this process. Okay, doing this process, it will be like n log n. It will go n log n, because we are doing square rooting, which also takes log of n time. Okay, so we'll try to code it. See now what inputs are there. We have to take n as input and n numbers. So here what we'll do, we know that what we need numbers till 10 raised to 6. So I'm pre-computing these numbers. Okay, now I have already array. Okay, which is size of 10 raised to 6, and uh, after computing this, now we know that the specific number is prime or not till the range of 10 raised to 6. Now we'll take input for m, and for int I equal to 0, I is less than I plus plus. We'll take a number. Okay, we have to take long, because the number will be till 10 raised to 12, and the range of int is around 10 raised to 9. Okay, we have to take long here. So now I have a number. Now I have to check whether the number is perfect square or not. Okay, so I what will be the root? Their single function. Okay, square root of x. Okay, now how we can check if root into root equal to x. Okay, then it's the it's perfect square. Let's see how. See, if we have number 3. Okay, what is under root of 3? 1.723 something. Okay, and the data type what we are using long, it will round off this to the 1. Okay, and after we do 1 into 1, it will be the 1. Is it same as this? No. So this is not a perfect square. Consider another case, like take 16. Okay, 16. So what is under root of 16? It's 4. It's a perfect number 4. Okay, and when we do 4 into 4, it will give us back 16. See, so if root into root x, now we know it's possible. Okay, it's possible. Here we know it's possible, and in else we know that now it's not possible. So what we'll do, see out no. Okay, now here we have to do another check. If sieve of root equal to 1, then see out yes, and another case will be see out no. Okay, now we'll run this on the given test case. Yes, no, no, is it right? Yes. Let's submit it. My compilation error. Oh, it's C++11. Okay. So I hope you understood this concept. Okay. The concept of sieve. Now what we'll do? We'll do a small variation of this. Okay. Like uh, an application of sieve. Like we can say like that. Okay. We can say like that. It's an application of sieve. See. We had, okay, I'll write down from 1 to 25. Let's write it down again. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Let's take till 30. Okay. Now what we have, what we can, okay, before that, what are we going to do here? Okay, so see, now what we need, consider like that, we have number n and we want to know its smallest prime factor. Okay, like this is our requirement. Okay, okay, like most of the time, nobody directly asks for smallest prime, no, prime factor. Okay, like we require it, okay, to solve a bigger problem. So this solution work as a sub solution for a bigger problem. Okay, so finding a smallest prime factor becomes a sub problem in so many cases. Okay, so what we have to do, we have to find smallest prime factor of number n. Okay, so how we can use sieve? So what we saw last time, okay, one is not, okay, right. For 2, what's the smallest prime factor now? 2 itself. For 4, it's 2. Okay. For 6, it's 2. For 8, it's 2. For 10, it's 2. For 12, for 14, for 16, for 18, for 20, for 22, for 24, for 26, for 28, and for even 30. Okay, we have 2 as a small prime factor for all those numbers. You can cross check. Why? Because what we are doing, we are going in a linear way from 1 to all numbers, and if the number is prime, what we are doing, we are cutting down, deleting the numbers which are multiple of it. Okay, so 2 will be multiple of 4, 6. Okay, so in this line 2 is the first number, it's the smallest number. So even consider this number 6. What are the prime factors of 6? 2 into 3. But which is the smallest? 2. Why? Because in this line 2 came first. Okay. Now when we'll do deletion for 3. Okay. Here what we got? 3 is a prime number because it's it it's not deleted. Okay. So 3. Now 6. But 6 was already deleted here and we assigned 2 value for it. Why? Because the smallest prime factor for 6 is 2. We'll move on. Okay. Now 9. 9 has 3. Then 15, it has 3. Then 21, it has 3. 23, 25, 27, 3. Okay. Then go to 5. What will what will be for 5? 5 itself. Then 25. For 7, nothing is there for 7. And in this case also, okay, what is square root of 30? We are going less than equal to. So it will be something 5 point something. Okay. So we are only checking till here 5. So what we have to cross check now? Does any prime number exist after 5 which has multiple before this range 30? Does 7 have anyone? No. There's 14, 21, 28, but those are already deleted. Okay. For 11, same. 22 deleted. 33 don't exist in this range. 13, 17, 19, 23. All numbers. Okay. So now we have to code this thing. Okay. We have to code this thing where what we are doing last time? Our sieve of I was either 0 or 1. 0 was not not prime and 1 was that number is prime. But instead of what we are doing here, sieve of I will be x, where x will be the smallest prime factor. Okay, we call it SPF also. So let's make some changes in the code. Okay, here see. Now what we'll do, uh, we can keep one. We can keep one. Okay. Okay. No, I will not write it from start. Okay. I'll explain just. Okay. We can take anything here. Okay. 1, 0, whatever we want. Okay. Let's keep 1. Okay. And from that, what we can say, if c of I equal to 1, it means its prime number. Okay. It's prime and its SPF will be itself. Okay. Now, mm, here, if the number is prime, okay, then we'll start to assign its multiples. Okay, the SP of its multiple will be that number I. Okay, but what case we saw last time, that for 6 We already assigned 2 here, okay? And when we were iterating for 3, 3 also 6 will come here, okay? Okay, it will not come because we are going to start from 9. Take another number like 12, okay? Take 12, okay? 12 was already got deleted and we assigned 2 as its SPF, okay? Smallest prime factor. So when 3 will iterate from here, 9 to, after that it will go to the 12. We don't have to change here, okay? We don't need to do any change here. If we'll assign 3 here, the answer will be wrong, okay? Because it's not smallest prime factor of 12. So what we'll do, if s of j, okay, c of j equal to 1, okay? Like we didn't assign any smallest prime factor to that number, okay? Then only we'll assign Sieve of j equal to I. Okay, I will be the smallest prime factor here. Everything will remain same. Okay, nothing will change. But we have to be careful for this case. Okay, 1. When there is one value for someone, it means it's prime and it's now its SPF will be itself. Like in this case, it will be the I. Okay, SPF will be the I. Now we must cross check does our answer is right or not. So what we'll do, for int I equal to 2, I is less than equal to 30. Let's say we'll go till 30 only. I plus plus, okay, I equal to 2 will output I and its SPF also. Let's see. Hmm, see, 2's SPF is 1. What does it mean? That 2 is a prime number and its SPF is 2 itself. Okay. Now what we'll do? We'll make a change here. If Sieve of I is not equal to 1, we directly print value of Sieve I. Okay. But in case of else, what we'll do? We'll we'll print I and I. Okay. Now let's run it again. Hmm, see, 2 smallest prime factor 2, 3 is 3, 4 is 2, 5 is 5, 6 6 2. Okay. See, here 3 didn't change 2. Even for 12, 3 didn't change the value because what we are doing, we are checking that if the sieve of that number isn't changed yet. What does it mean? It means that we whatever number we are iterating now is the smallest prime factor of j. Okay, so for 13, 13. For 15, it's 3. Okay, not 5. It skipped for 5. Actually, it already skipped for 5 because we are starting from 25. For 25, it will be 5. See, for 27, it's 3. 29 is a prime, it's 29. So this code works. Okay, so what we covered now, we covered smallest prime factor. Mm, there's another advanced thing here. Like recently, I told you that nobody asks directly for smallest prime factor, like print smallest prime factor. Okay, actually we use smallest prime factor for solving a sub problem. Like take something like this. Okay, we have number 20 and its prime factors are 2 into 2 into 5. Okay, so if I have 20, I have its smallest prime factor 2. Okay, and I divided it. Now the number will be the 10. 10's smallest prime factor is 2. If I divide 2 with 10, it will be the 5, and 5's um, smallest prime factor will be the 5. Okay, and after dividing 5 by 5, it will be the 1, and it will stop at 1. Now see here, what we got? We got this same thing. Okay, so uh, what's the other process of getting this thing? What we do, we make a map of int comma int. Okay, and we do like np of I plus plus, like whenever this number gets divided, like we starts from 20, we divide it with some number. Okay, so when we have to do like for so many numbers, okay, then we can use this thing. If we have to do with one number, we can do this thing. Okay, but we have to do with so many numbers, like we have from 1 to 10 raised to 6 numbers. Okay, we can do just this type of operations on every number. Okay, so instead of that, we create this SPF array, SPF vector, smallest prime factor is vector, and we then iteratively divide with SPF till we get 1, and whatever numbers we get, uh, those numbers are nothing else but prime factors of the number. Okay, I think we'll move to the code. So now what's the problem here? The problem is, mm, here we assign 1. Okay, we assign 1 for the numbers which are prime number. Okay, because we are iterating for from I into I. So now if we need s like we have to do factorization, we can still keep this thing. Okay, we can still keep this thing. What we have to change here now? See, uh, here what we'll get, 5 is prime number, so here SPF will be 1. Okay, like if we think about the last code, okay, which I had written few minutes ago, here it's 1. Okay, so whenever we'll get this 1, we'll add this number also, because we know that SPF of this number will be itself. Okay, we can make this condition. Okay, this is possibility 1. Whenever SPF is 1, add the number in list. Okay, list of prime factorization. Another is, instead of starting from I into I, we can go from I itself. Okay, uh, I think this is better. According to time complexity will be the same, and we just add add will add this condition. Okay, an extra condition, but here we are going to increase the time complexity. So what we'll do, we'll take a number, anything, any number, take a big number, some number m equal to, 10347. Okay, let's take this number, and what we have to do, no, we'll take something even number, and what we have to do, we have to print its prime factors, okay, all prime factors. Like we'll print multiple times also. Like in this case, what was it? 2 into 2 into 5. So we printed two times. Okay, we'll print it. Okay. So what will be the here? What in the first case it will be the while m is not equal to 1, because what we know, at the end we are stopping at when the number becomes 1. Okay. So while m is not equal to 1, see out sieve of m. Okay. In sieve we have smallest prime factor, and what's the next step we are doing? We are dividing m with its SPF. Okay, this is the case. But what was the first point was here? When SPF will be the 1, okay, we have to add m. We have to print m instead of its SPF. Okay, because its SPF will be the 1. So what we'll do, if sieve of m equal to 1, see out m, and in else it will be the sieve of m. Okay, let's run this code. Oh, come on. Mm, where we are failing? Yes, okay. M by equal to, the problem was that, see, for phi we have 1, okay, and in this line, okay, the line 27, what we are doing at this point, okay, when we reach to the phi, we are doing m equal to phi by its SPF, which is 1, okay, which is keeping it as phi. See, so phi will never reach to the 1, and will just get in that infinite loop. So what we have to do, when uh, we have sieve of m equal to 1, what we'll do, m by equal to m, okay, and in all other cases we are going to do this thing. Now run it. See, 2 into 2 into 13 into 199 should be that number. Okay, so 2 into 2 into 13 into 199, so it is 10,348. See, this is the same number. So this is actually the application of SPF. Like with SPF, what we can do, we can efficiently now efficiently what we can do, just get any prime factorization, okay, from this range. Okay, we have SPF till this range. Okay, I have to just change number here, like anything, 1 2 3 4 5 6, even is it 6? Yeah, okay, for even 1 is 6. See, this is the representation. 5 times 2, 5 times 5. So This is the application. From where it started? It started from Sieve. From Sieve, we got to the smallest prime factor, which is SPF. After that, what we did? Uh, Prime factorization. Okay, this is this is how we got here from here. Okay, first we had just boolean values. Is it prime or not? We just made some changes. Okay, after that changes, what we had, smallest prime factor of that number instead of just its prime or not. After that, we use the mathematical concept, and with that we try to find out the prime factorization of the number. Okay, so this is it. This is for today. In next, what we'll cover, maybe divisors, something related to divisors. I'll try to find some problems related to this where we have to use concept of smallest prime factor or prime factorization, and we'll try to solve those problems also. So that's it for today. Thank you.